Previously, we looked at the velocity and thermal boundary layer over a flat plate. Here in this lecture, we will look at the formula to estimate convective heat transfer coefficient for laminar and turbulent flow. The first one is boundary layer over an isothermal flat plate h of x convective heat transfer coefficient in the boundary layer over an isothermal flat plate. So let's assume we have a laminar flow over the flat plate. And this is our plate. And this plate, assuming that everywhere you are keeping at a constant temperature of Ts, and there is a cold stream that comes over the plate. It could be the other way around, a hot stream going through the plate at the Ts, which is less than T infinity, or the fluid with the U infinity, T infinity. And what we did last time, we are looking at the velocity profile in the boundary layer, U of y, and similarly we were looking at the temperature profile. The way to T infinity or T of y. Now, we discussed that the Blasius could develop a velocity distribution or u of y by solving momentum and continuity equations, and he did it numerically. He got uy, and ty can be also found by solving energy equation in the thermal boundary layer. And recall that when we were discussing about this boundary layer, we said that the heat flux from the very first layer of fluid close to the plate is going to be by conduction. It means there is a zero velocity, which is correct since we have a no slip boundary. So what we could say here is that the conduction that was happening close to the plate, dt dy at y equal to 0, which is the solid surface. The heat is dissipated to the fluid by convection, h of Ts minus T infinity. And from here, we were getting h equal to minus k dt dy divided by Ts minus T infinity. Now, in order to get h, the convective heat transfer, we need to have the thermal distribution, temperature distribution, T as a function of y. Similarly, we need to know about the velocity profile u of y, and by having them, we can develop an estimation for h. Now, the result of the solving momentum and continuity equation, we could get the thickness of boundary layer, delta. As a review, it was 5 x Reynolds of x to the power of minus 0.5. And then we said that the thermal boundary layer is related to the velocity boundary layer, or the thickness is related to each other. The thickness, and it's going to be, the ratio is going to be Prandtl number to the power of 1/3. Now, having uy and t of y, we can get the h of x, the convective heat transfer at any location at any x is going to be 0.332 k Prandtl to the power of 1/3 u infinity divided by mu x to the power of half. Notice just the similarities between the Prandtl exponential coefficient 1/3 here, and mu is the kinematic viscosity, or mu over rho. That's the properties of fluid, and this is the local convective heat transfer coefficient. So if we are looking at this flat plate here, and assuming that X starts from here, then we consider a small element here, and we are looking at the HX here, and we are evaluating HS at this location, let's say at any of X. So it's going to be a function of space here, and it's changing along the length of the plate. Now, if we look at the Nusselt number here, Nusselt number is going to be a function of X as well. It's going to be HX X divided by K. That's a local Nusselt number. K was the thermal conductivity of fluid, and Hx is the local heat transfer coefficient, and X is a characteristic length. And here for the flat plate, in this case, is going to be distance from the edge. Now, if I replace Hx here, our Nusselt number would be 0.332 K Prandtl 1/3 infinity mu x divided by half times X divided by K. So Nusselt number of X, this term by this term cancel out. We have X here. If we do the math, what we're gonna get is 0.332 Prandtl to the power of 1/3 Reynolds of X to the power of half. This is the local Nusselt number that we can get, where Reynolds number of X was U infinity X divided by nu. And this is the Reynolds number evaluated at the X location. So this is the Nusselt number for the laminar boundary layer. Boundary layer. So flow should be laminar to be valid. In order to be laminar, Reynolds X should be less than the critical Reynolds number for transition from laminar to turbulent is 5 times 10 to the power of 5. And Prandtl number should be less than 50, greater than 0.6. In your text, you would see probably sometimes it just refers as a 60, but it's acceptable range actually for the Prandtl number. Now, this gives you the local coefficient for heat transfer, but this is the local, but we are interested at the overall heat transfers that's happening here. At the overall heat transfer. So we need to find the average heat transfer. We need an average H here. H of L average is going to be 1 over L. L is going to be the length of the plate. So for this plate that I'm assuming this is, let's say X, this is X equal to L. So I'm looking for an average coefficient of heat transfer, convective heat transfer for the length of the plate. And it's going to be 0 to L, Hx dx. So if we do the replacement, 1 over L, 0 to L, Hx is 332, Prandtl number to the power of 1/3, U infinity x nu to the power of half dx. Now, the only term that depends on x is just here, this small x, that if we do the integral of that, we're going to get 1 over L times 0.332 Prandtl 1/3 U infinity nu half, and the integral of 1 over x to the power of half is going to be 2x power of half from 0 to L. If we replace for L, we're going to get 0.664 Prandtl 1/3 Reynolds number at L, at the rear edge of, or at the end of the plate, to the power of half. So and everything is going to be divided by L. You would have one extra L. So this is going to be the overall heat transfer coefficient. Now, if I compare this one with the definition of, or with the formulation for the h of x here, then what you're going to find out is this average heat transfer coefficient is going to be 2, the local heat transfer evaluated at the rear edge of the plate. So the significance of this is the average heat transfer coefficient at the laminar boundary layer is 2 times or twice of local transfer coefficient at x equal to L at the end of the plate. Similarly, we can get Nusselt number. Average Nusselt number is going to be HLL divided by K. And if we do the replacement, it's going to be 664. Prandtl number 1/3. Reynolds number half. And this average Nusselt numbers, I'm just putting the index of L because you can find the average over any specific portion of the plate that we want. This is going to be 2 Nusselt number, local Nusselt number evaluated at x equal to L. Now, if we pay attention here, this is Prandtl number. This is a function of C, mu, K, all fluid properties. Reynolds number is going to be function of rho and mu. So these fluid properties are temperature dependent. So these are fluid properties and temperature dependent. So the question here is that at what temperature do we evaluate these properties? So fluid properties evaluated at what temperature? So if you look at this flat plate that we have, we assume this is at Ts, and then we have flow at T infinity. So there is a variation of temperature in fluid from Ts to T infinity. To do the evaluation, we use a temperature called film temperature. So we are evaluating at film temperature, Tf, which is an average between the surface temperature, T infinity divided by 2. So all the properties, rho, C, K, mu, all are evaluated as a fluid temperature or average film temperature. And the same, similarly, what we can do here is just a reminder, recall that similar to this heat transfer coefficient, we can find friction coefficient for in the laminar boundary layer by solving the continuity and momentum equation. And we were showing that one C of f of x is going to be tau of s of x. This is the local shear stress, so wall shear stress divided by u, rho u infinity to power 2 divided by 2, which is going to be 0.0 664, local Reynolds number to the power of minus 0.5, and the average one, average friction coefficient C of F of L, on average, what you're gonna get is 1.328 Reynolds of L and the power of minus half.